Okay, statistics students, I'm going to walk through one good example of how to conduct a one-sample t-test on the mean of some data. So we're covering a couple new things. First of all, we have data instead of statistics. So we will first type these 12 numbers into our graphing calculator at some point. And we'll need that in order to do the calculations. So first of all, though, we want to read through the problem. There's a claim that a radio station plays an average of 50 minutes of music per hour. However, you turn on the radio a lot and it seems like there's always commercials playing, so you have a suspicion. Now you'll notice in this problem you don't ever see the word greater than, less than, or different. So you just have to think logically. If you are hearing a lot of commercials and there's a claim of 50 minutes of music, then it would seem that the station is playing less music than they claim. And so that's going to come up later in our alternative hypothesis. So they're claiming 50, but you are suspicious that maybe it's less. Those will be our two hypotheses, which usually is the first step. So the null hypothesis is sometimes considered the dull hypothesis, like if nothing's going on, if everything is happening like it's supposed to. If they are doing what they claim, then the mean number of minutes in the population is 50 minutes per hour. But since you've been turning on the radio and hearing a lot of commercials, you're suspicious that maybe the mean is less than 50 minutes. That would be the logical counterclaim. And then we want to define mu. Mu is the mean minutes of music per hour at this station. That's what we're testing. They claim the mean number of minutes of music per hour is 50. We're suspicious maybe it's less than 50. Those are our hypotheses. So then the conditions, same three conditions that we've checked for intervals. So it's kind of nice. We can just remember back to intervals. First of all, we have to have a random sample. And somewhere up there it said it randomly selected. So we could just say the sample is random. We also want to check to see that it's a big enough sample to assume a normal sampling distribution. Well, that's a bit of a problem because the sample size is only 12. So we know the sample size is less than 30. But we might still be okay if we can presume that maybe this data could have come from a normal population. So what we have to do is graph the data. So again, you can always push pause and type the data in, do a stat plot. I would suggest a histogram. And remember too, if the histogram looks suspicious, which I believe this one kind of did, it looked like it might have an outlier, you can always go to Window after you make a graph, and the X scale can be changed to a smaller number, and if you change it to a smaller number, you'll get a slightly different view of the histogram. And when I did that, then it looked like there was no problems. So I'm just going to graph the original window. When I did like a zoom stat, the original window produced a histogram that looks something like this, and there was a little gap. But again, when I checked it with a smaller X scale, then it looked like that was not an outlier at all. So n is less than 30, but a histogram of the data showed no outliers or heavy skewness. As long as we don't have any outliers or heavy skewness, it's not unreasonable to believe that this sample came from a approximately normal population. And if that's the case, well, then we can have a small sample size and we can be okay. Just make sure that you do include a sketch of your histogram. That is necessary for full credit. You cannot just describe it. You have to actually show a little sketch. And then the third thing to help guarantee independence is that n is less than You know what we should say, I guess. Just something like surely, because that really is an assumption. Surely, 12 hours is less than 10%. So surely 12 hours is less than 10% of all hours at the station. And therefore, we can proceed with whatever this is called. This is going to be called a one-sample t-test. Now, it's one sample because we just have one sample. We have one set of data. There's 12 numbers up there are one set of data. That's important because later we will have two groups, two sets of data, or maybe two experimental groups, and we will want to compare whether one mean is higher than the other mean. So it's important that we name these things correctly. This is just a one sample test. Later we may have two sample tests, but right now we just have a one sample test. And so far, right now, after all that work and writing, we've only earned 2 points out of 4 points on an AP test problem. So we've got a little more work to do, but it's a lot easier from here on. That's the hard stuff. First of all, we want to calculate the t-test statistic. The t-test statistic is very similar to the z-test statistic. In essence, it's a z-score. We want to take our actual, well, I shouldn't say actual, we're going to take our sample mean, which is what we really got, so I suppose it's actual in that sense. Our sample mean was 47.9. That comes off of our calculator when we run the t-test. And we want to find out how far away that is from the mean. Well, the mean was assumed to be 50. But we want to find out what it is in a standard way. In other words, how many z-scores, how many standard deviations. So we have to divide by the standard error. The standard error is the standard deviation of the sample, which off the calculator was 2.81. And we divide by the square root of 12. I wrote that all down because on multiple choice questions, sometimes they will ask you questions of this nature where the formula is going to be the answer that you're looking for. And so what they'll do is put, ones that are close but not quite. They'll say 50 minus 47.9, which is wrong, or they'll forget to put the radical 12 in the denominator, which is wrong. So they'll give you some choices on multiple choice that are incorrect. So it's good to know the formula that you would use. The bottom line, though, for a free response question is to write down the correct t-test statistic. So that number can be put right off of your calculator. But I showed you this just to show you what the work is behind the scenes that gives you the negative 2.57. That's pretty far away, isn't it? 2.5 standard deviations seems to be pretty far away. So the p-value you would expect would be fairly small, and it is. Off the calculator, the p-value is 0.013, so just a tick over 1%. That's fairly unlikely. So we're going to conclude that because the p-value is less than the alpha level, which we were not given one, so we will just use 5%. So since the p-value is less than an alpha level of 5%, the statistical conclusion is we reject the null hypothesis. What this means in a practical sense then, which is always what we finish with, we say something like there is convincing evidence that the mean, here's where you just kind of copy and paste some of the stem, the mean minutes of music per hour at the station is, now remember, we rejected the null hypothesis. We rejected that. Well, if you reject that, then you must believe the alternative. So we conclude by saying it's less than 50 minutes. The mean music is less than 50 minutes. That's our conclusion. And it's convincing because the alpha level is, or the p-value is less than the alpha level. So when you get low p-values, you reject HO. When p is low, reject HO. When p is low, reject HO. And just one last little tidbit. In the conclusion, you have to make sure you always have LCD. L is the linkage. The linkage is what you made your decision on, and we wrote that at the very beginning, because the p-value is less than alpha. That's the linkage back to the evidence. So just like a lawyer, you go back to the evidence and you link the evidence to your conclusion. Because the p-value is less than alpha, we reject HO, which was the decision. So the linkage was the because part. The decision was we reject HO. And then that whole last sentence was the context. The context is about the mean minutes of music per hour at the station, and we believe it's less than 50. So those are the three components of the conclusion. This is a complete t-test, top to bottom, all 4 steps, all 4 points. That's what you want to show when you're doing one of these. The very next problem has data as well. This is a slightly different question. It's about, I guess that they took the radar gun out to a construction zone to see if cars were driving over 25 or not. And so it's a t-test, and it's very similar to this one, except this time they actually told you to look for if it's greater than 25. That would be what we suspect. If we're less than 25, we don't worry about it, but if we're greater, that would be speeding, and that would be dangerous to the construction workers. So this is one that I'm going to let you do on your own, and I think I'm not even going to give you, I probably should give you something. So let me just tell you that on this one, you will reject the null hypothesis. I'll just leave it at that. So when you get to the end of this, you should have a low p-value, and you should be rejecting the null hypothesis if all goes well. So go ahead and do that one. And as always, let me know if you have questions, and hopefully I'll see you soon in class.